A vector is an object that has both magnitude and direction. The length of the vector gives the magnitude of the vector. Here's one way to represent a vector. The tail of this vector is at A, the head is at B, so we can call it AB and write an arrow over it. We could also use a letter that's underlined, or a letter in bold. The magnitude of a vector, that's the length of a vector, is shown like this, with vertical lines on either side. So the length of this line AB would be given by this. Or if we're calling our vector little a with an underline, we have vertical lines on either side to represent its magnitude. Or we can just write down the letter without the underline to represent the magnitude. Here is the vector a. The vector minus a is a vector that points in a direction opposite to vector a. Both of these vectors have the same length or magnitude. Let's see some examples. In this first example, an object is subject to two forces. One force of 3 Newton downwards, vertically downwards, and one of 8 Newtons horizontally to the right. So this arrow here has a length of 8 units. This arrow has a length of 3 units. So these two forces act on this object. In example 2, we have an arbitrary vector f. The vector minus f has the same length or magnitude but points in the opposite direction. In example 3, we have two equal vectors p and q. Two vectors are equal if they have the same length or magnitude and if they point in the same direction. In example 4, f with the underline is a vector. F without the underline is the magnitude or length of vector f. In this example, an unmanned vehicle moves on tracks around a factory floor carrying components from the store at point A to workers at point C. The vehicle could go directly from point A to point C, or it could go from A to C via an intermediate point B. So the movement of the vehicle could be represented by these displacement vectors. The movement of the vehicle from point A to point C directly could be represented by the displacement vector AC, tail at A, head at C. We could also represent the movement of the vehicle as the sum of two displacement vectors, AB and BC. We say that the sum of vectors AB and BC is vector AC. So if we want to add this vector onto this vector here, we just join the tail of AB to the head of BC. So this is called the triangle law for summing two vectors. Here's another example. Suppose we want to add these two vectors. Now we're using the other notation. In this notation we are not referring to the endpoints of the vectors. Now to sum them, we join the tail of one vector to the head of the other vector. So we can join the tail of B to the head of A, and then to get the sum we just join the tail of A to the head of B, and if we call that vector C, then vector C equals vector A plus B. Let's take this example here. We want to add vector A and B together, so we could take B, move it parallel to itself so that its tail is at the head of vector A. So it would look something like this. Then to get vector A plus B, we just join the tail of A to the head of B. Now what's interesting is that we can move vector A so that its tail is at its tail is at the head of vector B. So we could move A parallel to itself. So this is meant to be vector A. Now to get the sum of these two vectors, we join the tail of B to the head of A. So here is B plus A. But A plus B, vector A plus B is the same as vector B plus A. They point in the same direction and they have the same length. These two vectors have the same length. So this shows that addition of vectors is commutative. It doesn't matter what order we add the vectors in. Now this commutative law comes from the fact that opposite sides of a parallelogram are equal in length and are also parallel. So if this is vector b, then this vector over here is also vector b, because if I complete this parallelogram, then the opposite sides point in the same direction. They're parallel. That's the meaning of a parallelogram, but they're also equal in length. Opposite sides of a parallelogram are equal in length. So if this is b, well, if this is b, then this opposite side is b. Similarly here, this is vector a. So I could add like this: b plus a gives me this diagonal, which is the same as a plus b. Suppose we have three vectors a, b and c, and we want to add the three of them together. Now it turns out it doesn't matter which two vectors we take to add together. First of all, we could add b and c together and add the result to a, or we could add a and b together and add the result to c. Let's suppose we add b and c together. Well, we apply the triangle law. We join the tail of b to the head of c. Next we want to add a onto b plus c. So we join the tail of a to the head of this vector. This red vector is b plus c. So we get our result a plus bracket b plus c. Now let's suppose we add a and b together first. Well, we get this vector here. If we want to add this vector onto c, we join the tail of it, the tail of a plus b, onto vector c. And as you can see, we get the right hand side here, showing that vector addition is associative. By the way, we can write a plus b plus c like this. We can swap positions for b and c, because vector addition is commutative. And then we can apply the associative law here and move the brackets. So we get a plus c plus b. Now this doesn't appear here, but this is also true. If we add a onto c first of all, well, to do that we would have to move vector c parallel to itself. So move c here. So then to get a plus c, we'd have to join the tail of a to the head of c. So here's vector a plus c, and finally we would have to add that onto vector b. So we'd have to move this parallel to itself, so it's up here. So a plus c is over here. And finally we join the tail of b to the head of a plus c. And this vector is the same as this vector here. Here we have a force F1 of magnitude 2 newtons acting vertically down on object A, and a horizontal force F2 of magnitude 3 newtons acting to the right on object A. It turns out that the resultant force on this body is the vector sum of these two forces. That's something proven experimentally. So we could move this force parallel to itself, so its tail is at the head of vector F1, so it's along here, and then join the tail of F1 to the head of F2. Or we could complete a parallelogram and drawing the diagonal. So the resultant vector R is the vector sum of the two forces. We can get the magnitude of vector R using Pythagoras' theorem. So we see that vector R is the hypotenuse of a triangle of sides length 2 and length 3. So R is going to be root 2 squared plus 3 squared. That's root 4 plus 9, or root 13. So the magnitude of R is root 13 newtons. We could also get the direction, well, the direction relative to the horizontal, by calculating angle theta. Now the tan of theta is opposite over adjacent. That's 2 over 3. And from that we can calculate theta. Suppose we have this force F and we want to consider components of it in the horizontal and perpendicular direction. Well, we can imagine that F is the hypotenuse of a right angled triangle. Then the cos of theta is the adjacent over the magnitude of this. So, well, the magnitude of F is just F without the underline. So cos of theta is adjacent over F, which means that the adjacent is F cos theta when we cross multiply. The sine of theta is opposite over the hypotenuse, opposite over F. So the opposite isn't shown here, but that means the opposite is F sine theta. So F without the arrow, or the underline, is the magnitude of vector F. So a force F in this direction Well, a force of magnitude F in this direction is equivalent to a force of magnitude F cos theta to the right and F sine theta vertically up. So we can just add these two forces by the parallelogram or triangle laws to get back our force F. So here's an example. Here F is 5 and the angle is 30 degrees. So the horizontal component of this force has magnitude 5 cos 30 degrees. And the vertical component has magnitude 5 sine 30 degrees. So here's another example. The horizontal component is 15 cos 40, which is 11.5 newtons. And the vertical component is 15 sine 40, which is 9.64 newtons.